Okay, we move the next speaker. The next speaker is Professor Sebastian Engelke. He is a assistant professor in University of Geneva. And his research interests include extreme value theory, risk assessment, spatial statistics, and machine learning. So today, his talk is on causality for extreme values. Let's welcome for Professor Engelke.
Okay, now you should be able to see my screen.
Yes.
Okay, so thanks for the introduction and the invitation. And yeah, my name is Sebastian Engelke. I'm at the University of Geneva, and I will talk about causality for extreme values. And this is joint work with various great colleagues of mine, which I noted down here. So let me first say a couple of words where I come from. So my background is extreme value theory. And well, we are concerned with the analysis of rare events, extreme events, which have typically very small probabilities, but which can still have serious impacts on our health, on the environment, on the economy. And down here, you can see several of examples of extreme events, so flood event, a financial crisis, or a heat wave. And in all of these examples, we might have data. And as a statistician, of course, we would like to model this data with some distribution. Now, in extreme values, we are mostly interested in the extreme events, which can be found in the tail of the distribution, so this red part here. And you can already see the statistical difficulty, namely that we only have very few observations in this tail. And that makes inference difficult. And usually we have to rely on asymptotically motivated approximations similar to the central limit theorem, but now adapted to extreme values. So while this was a univariate example here, of course, one can think about multivariate problems where we have p variables and we want to understand what is the dependence between extreme values of the single components. And really, a lot of work in multivariate extreme value theory is concerned with this modeling of extremal dependence of a random vector x. And nowadays, of course, people are interested in going into higher dimensions, and there are now many new methods how to introduce sparsity in extremes. And we've written a review article on some of these methods, which appeared in the annual reviews this year. Now, one way of introducing sparsity, of course, are conditional independence structures and graphical models. And we have made this link between the classical theory of graphical models and the theory of multivariate extremes in this 2020 discussion paper in JISSB. And now all of these methods here, they really are concentrated on modeling extremal dependence and not so much in detecting causal structures. So, of course, in this conference and also in general, there's a high interest in causal attributions, and especially in times of changing climate, weather extremes, financial crisis, there is really a lot of public kind of attention on trying to give a causal meaning to extreme events and to find out which are the causal drivers of say climate extremes like heat waves or floodings. And somehow there at this interface of extreme value theory and causality, there are two different perspectives. So the first one is, well, we could say that if we see extreme events, then probably we'll see the causal relationships even more profoundly or more directly than we would see them in the bulk of the distribution. So we could use extreme observations to do causal discovery. From a slightly different perspective, we could also say we're actually only interested or mainly interested in the effects or treatment effects on extremes, so on very high quantiles, which is the case in climate extremes, because there really we want to know how does climate change affect very rare events like 1 in 100 year storms or heat waves. Okay, so there's really an interest in combining the theory of extrapolation from extremes and causality. And I will talk about two contributions that we have made. So the first one is on causal discovery, which appeared in the annals, and the second one is on estimation of extremal quantile treatment effects, which is still a preprint but should be out in the next few weeks. Okay, so let me start with the first part. So the setup is somewhat similar to the setup in Lingam. So we look at a heavy tail, a non-Gaussian, heavy-tailed structural causal model, and we'll restrict our attention here to linear structural causal models that are defined on some underlying unknown DAG. And heavy-tailed here means that our noise variables are actually heavy-tailed, and that means that the survivor function decays like a polynomial with some index gamma, which is called the extreme value index. And this really means that the whole this whole p-dimensional distribution has a heavy tail, and this is often relevant because like precipitation and other meteorological variables exhibit these heavy tails. Okay, now let us first, we kind of want to use now the extreme values in this structural causal model to identify the causal order. And let's first look at just two variables and see how we can do this. So we want to define a coefficient called the causal tail coefficient and use the asymmetry in this coefficient to identify the causal direction. So this coefficient gamma 1, 2 would be defined as the conditional expectation of f2 applied to x2. So f2 is the CDF of x2, given that we see an extreme value at an extremely large value in the first variable. Okay, and we will push the level of extremeness, so the quantile level, we'll push this to the upper endpoint of x1, and the limit we'll define as this causal tail coefficient. Now, of course, we can change the roles of x1 and x2 and get the coefficient gamma 2, 1. Now let's try to give an intuition why this actually helps us to identify the causal structure. So here's a simple example where x1 causes x2 in a very simple way. And now to compute this coefficient, we have to condition on the fact that x1 has a large value. And then we look at the values of x2. And we can see in this example here that x2 is then also large. So in the scale of x2, if x1 is large, then x2 will also be large. And that means that this value here will always be close to 1. And in fact, one can show that in the limit, this coefficient gamma 1, 2 will be equal to 1. On the other hand, if we change the roles of x1 and x2 and compute gamma 2, 1, then we condition on the fact that the x2 is large, and we look at the values of x1, whether they are extreme or not, and we can see some are extreme as well, but others are actually in the bulk of the distribution of x1. And the reason for this is that if x2 is large, well, either x1 was large, that means, well, x1 is large, or actually the noise epsilon 2 was large, but then the value of x1 is independent, and we basically just see something in the normal range of x1. But this also means that then this value here will be strictly smaller than 1, and we can show that even theoretically, that then this value gamma 2, 1 is strictly smaller than 1. So this means there's an asymmetry, and that asymmetry based on extreme events helps us to identify the causal direction between x1 and x2. Of course, there are different causal structures, and for two variables, I listed all possible structures here. So basically, we can have independence, x1 causing x2, or x2 causing x1, and we can also have an additional unobserved confounder that might influence the two of them. And now we can actually show that the value of these two coefficients, gamma 1, 2 and gamma 2, 1, helps us to uniquely identify which of the 6 cases we have, or which of the causal directions at least we have. So if we have independence, then both coefficients would be equal to 1/2. If x1 causes x2, as we've seen in the example before, then gamma 1, 2 is 1 and gamma 2, 1 is smaller than 1, and the other way around, of course, for x2 causing x1. But even if we have unobserved confounding, we still can identify or can distinguish these 3 cases. So if we have independence plus confounding, then both coefficients will be strictly smaller than 1. If we have x1 causing x2 plus confounding, then we have the same kind of direction of the coefficients. So we still estimate the correct causal direction and the same for this example here. So really this asymmetry in the coefficient allows us to distinguish these 6 cases of causal structures. Now, of course, in general, we'll have p variables and would like to identify the causal order of these variables based on the coefficients. So here's an example for the causal order, but I don't think I have to introduce what this is. And well, this will be based then on not only these 2 coefficients, but for any pairs of coefficients of this p variable, pairs of variables of this p variables, we'll get this coefficient. And we then store them in a matrix gamma, a p times p matrix. And this will be the input for our algorithm called the extremal ancestral search, or the EASE algorithm. I cannot go into details into this algorithm. It's very computationally efficient. You can look at our paper if you're interested. But what we can actually show that if we put the true population gamma into as input of this algorithm, then this algorithm will give us back a true causal order. And this will actually remain true if we introduce hidden confounders into the structural causal model. The EASE algorithm will still have the oracle property and give us back a true causal order on the p observed variables. Of course, in practice, we will have to estimate these coefficients. And well, we assume that we have n independent observations of these p variables of this linear structural causal model. And since we're only looking at the extremes, actually, instead of n observations, we'll only use the kn largest observation. So just a small proportion of the extreme values. This is kind of a tuning parameter. And we then define a very simple non-parametric estimator of gamma called gamma hat. And then we use gamma hat actually as the input of the EASE algorithm. And this will give us then an estimation of the causal order of the p variables based on the extreme observations. And we can show that, well, if we choose this sequence Kn, which is the number of extreme observations that we use, this is also called an intermediate sequence. If we choose this in a correct way, namely that Kn goes to infinity if n increases, and Kn grows more slowly than n, then actually the EASE algorithm is consistent in the sense that with probability 1, we will estimate a true causal order on the p variables. In the paper, we also have 2 applications. One is on financial data and exchange rates, and the other one is on flood events and river networks. So I don't have time to go into detail here, but yeah, I invite you to have a look at these applications also in our paper. So instead, I would like to go on with the second part of my talk, which is on extremal quantile treatment effects for habitable distributions. So this is a completely different setup than before. So if you were lost a little bit, then this is the time to start listening again. So the setup, namely, is the setup of potential outcomes, where we have a binary treatment D and the outcome Y. And usually, as we've seen in this conference many times, people are interested in the average treatment effect, which is just the difference between the expectations of the potential outcomes. But often cases, people are interested in something else, namely how the treatment affects quantiles of the distribution. And this is why people have introduced the so-called quantile treatment effect, which is simply defined as the difference of the quantiles of the distributions of the potential outcomes. And examples for questions where this might be relevant is, for instance, how much does an education program increase the wage of the 0.1% poorest portion of people? Or how much damage does a 1 in 100-year heat wave cause if we were to double CO2 concentration in the atmosphere, for example, due to climate change? Okay, in both these questions and in many questions, we'll be interested in extreme events. So the influence or the effect of the treatment on very extreme events. So for example, here in this 1 in 100-year heat wave, often we might only have 20 or 50 years of data, but we're trying to estimate a quantile that goes beyond the range of the data. So this is clearly a question that is related to extreme value theory and cannot be tackled with just classical empirical estimation of these quantiles. So we will focus here on quantile treatment effects where the quantile level tau is very close to 1, meaning that we have very extreme, we're interested in very extreme observations. Okay, so we'll also use the notion of propensity scores when we have now an additional covariate vector x. Then the propensity score is defined as the probability of treatment given the covariate vector. And we make the common assumptions that we have unconfoundedness and that our propensity score is bounded away from 0 and 1. And now, without discussing this here too much, for the sake of time, but we will use throughout the so-called sieve method to estimate this propensity score non-parametrically. Oops, sorry. Okay, so now how do we estimate quantile treatment effects? Now, first in the classical case. So suppose we have observations of the outcome, the treatment and the covariate vector, then Firpo introduced estimators on the quantiles of the potential outcome distributions, basically as just an empirical estimator of the quantile, but adjusted by the propensity score. And well, then how we define the quantile treatment effect is the difference between the quantiles. And here I put actually 1 minus tau, because we will be interested in the upper tail. So if tau is small, then this will be very close to, or this will be quantiles very close to the upper endpoint. So they will be extreme, but positively extreme. If you're interested in the smallest values, so in the minima, then you could also just look at the quantile treatment effect at tau, but for tau very small. Okay, so now there are the classical way of estimating this quantile treatment effect is simply taking the difference between these adjusted empirical estimators. And Firpo showed an asymptotic normality of this estimator for some fixed quantile level tau. Okay, so this might not be actually the case of interest, because in extreme values we'll be interested in quantiles that grow with the sample size so that we can actually formulate mathematically what it means to look at extreme quantiles. So Zhang et al. Therefore also looked at quantiles tau n that where tau n goes to 0, so 1 minus tau n goes to 1 with n, and n times tau n goes to infinity. Now, why is this n times tau n important? This is important because n times tau n is the expected number of exceedances above the quantile 1 minus tau n in a sample of size n. So this means that by this assumption, he makes sure that there still are enough observations to estimate this quantile treatment effect in a classical way by just using empirical methods. And he also actually went a little bit higher and said, okay, we can look at kind of moderately extreme case where n times, and now I call this Pn, goes to some constant d. So the number of exceedances will converge to a constant. I call this here Pn because now later on, this Pn will be more extreme than tau n. And well, in this case, he derives a non-Gaussian asymptotic distribution because now he no longer has infinitely many samples in the limit, but only a finite amount of samples. But what we're actually interested in extremes is when the quantile of interest goes beyond the range of our data. So where the expected number of exceedances converges to 0. Okay, because a 1 in a 100-year event where we have 50 years of observation does exactly satisfy such a condition that we actually have no exceedances and we still want to estimate this quantile. And there we really can no longer use empirical estimates like here, but we need to use extrapolation theory from extreme value theory. So how can we estimate extremal quantile treatment effects? Well, we have to use an approximation, and our assumption here is that our potential outcome distributions are heavy-tailed, as we've seen before. So the tail behaves like a polynomial, And now for different treatment, we can actually have different extreme value indices here. Okay, we also have some theory for non-heavy-tailed data, but I will concentrate here on the heavy-tailed case because it's the most interesting one. All right, so how do we now estimate the quantile of a very extreme quantile? So Pn will be now a quantile level that is smaller, where Pn is smaller than tau n, and that can go beyond the range of our data. So from extreme value theory, we can actually derive an approximation for this quantile, this 1 minus Pn quantile. Namely, we can choose now an intermediate quantile tau n that is less extreme. Sorry? Okay.
Just go ahead.
Oh yeah, sorry. Okay, so what we can actually do, we can choose an intermediate quantile tau n that is less extreme than Pn, and that we're still able to estimate empirically. And then we can kind of correct this, this quantile to go to the more extreme quantile by some correction factor, which involves this extreme value index gamma j. Okay, this comes really from an asymptotic result from extreme value theory. And well, then we can estimate, or we can, the extremal quantile treatment effect simply as the difference of these two approximations. Okay, so how do we do now in practice? How do we estimate these quantities that we have here? Well, what we do, we simply plug in estimators for the intermediate quantile and estimators for this extreme value indices gamma j hat. Tau n here is this kind of tuning parameter, the intermediate quantile, that determines how many extreme observations we use in our estimator of this empirical quantity. And this should satisfy n times tau n goes to infinity, so that we have enough observations to do empirical estimation. And this will be exactly this adjusted quantile estimator that we have seen from FÖPL. Now for the correction, to really go to more extreme values, we need estimators of the extremal indices. And those are given by an adaptation of a classical estimator, the Hill estimator, but now for our causal setup. So the estimators basically are similar to the classical Hill estimator, but with an adjustment for using the propensity scores. Okay, so I'm not going into too much detail here. And then, okay, we can show, first we have to show the asymptotic or joint asymptotic normality of these causal Hill estimators. And we can actually do this under sufficient regularity conditions. And based on this, then we can show that the extremal quantile treatment effect for really extreme quantiles 1 minus Pn is asymptotically normal. So this is also different than in FÖPL that got a non-Gaussian distribution for his estimator. And we can also consistently estimate the asymptotic variance so that we can actually do inference for these extremal quantile treatment effects. All right, let me very briefly talk about an application. So we look at the effect of college education on very high wages. This was, or this data set was considered in Heckman et al. In 2018. Our treatment is whether a person went to college or not. And our response is the wage at age 30 in dollars per hour. And for a propensity score adjustment, we have several covariates like the region of residence, the broken home status, and so on. And here we have 800 samples. So what we can see here is that if we estimate the quantile treatment effect at the level of the 0.5% highest wages, then we clearly see a positive effect of college education on these very high salaries. And what you see on the x-axis here is this tuning parameter tau n, so which corresponds to the number of exceedances of the intermediate quantile. And we can see that for a wide range of these parameters, we see a significant effect. And how you choose this tuning parameter tau n is in extreme value theory is usually by certain stability plots, which I don't go into detail. So, but yeah, you can see the details of this this application very soon when we submit our paper on arXiv, which should be in the next weeks. And with this, I would like to thank you for your attention. Of course, I'm happy to answer questions if there are any.
Great. Thanks for the great talk. We still have a few minutes, so let's have a discussion. So is there any questions or comments for this talk? So let me ask a very simple question. I see that in the first part of the talk, when you estimate the causal relationship between the variables, you assume each of the residuals follow a heavy-tail distribution, right? So my question is, can you weight that assumption so that you have only part of them follows the heavy-tail distribution and the other follows some, for example, normal distribution?
Yeah, that's a good question. So this is really kind of a maybe strict assumption that we have here, that all these noise variables follow heavy-tail distribution. And actually in the paper, we consider cases where we have different tail heavinesses for the different noise variables. So in these cases, so for example, if you have Gaussian distribution, in some cases we can still identify the causal structure, but in some cases this will break down. So this is maybe similar to Lingam, where you need some non-Gaussianity to identify the causal structure. But we discussed this, it's a bit more subtle, so I didn't talk about this here. But yeah, we discussed this problem of having different tail heavinesses for the different variables. In some cases, we can still do something. In others, we can no longer identify the direction.
Okay, thanks. And also, when you distinguish the causal direction in the figure, for two variables, can you move to that page? You have 6.
So this one?
Yes. So here, it seems that you cannot distinguish if there is a hidden variable or not.
No, this we can not. In these cases, we cannot. Yeah. But maybe here it's more important to distinguish the causal direction, whether to distinguish between those two cases, right?
I see.
So, but yeah, this we cannot see whether there is a confounding variable or not. Yeah.
And also for the first relationship, x1 is independent of x2. Here you have the estimator of these two gammas is equal to 1/2. But for data, because they are samples, so you never have exactly 1/2. Do you have to some do some hypothesis testing? Yeah,
exactly. So also for these cases, actually, if we want to do some tests whether there's a causal effect or not, then we need to use some asymptotic results. And this is actually what we're currently working on to get asymptotic distributions for these empirical estimators. And then we will be able actually to test also all of these different cases. Mm-hmm. So that's a very good comment. Yeah.
Thank you. So do we have any other questions? Okay, if no questions, then let's thank the speaker again.
Yeah, thank you.